Welcome everyone to this week's STEM Talk, an online series for aerospace families brought to you by fellow aerospace experts. I'm Michelle Klinker from Aerospace University, and with the support of Aerospace University, iLab, and Corporate Communications, I'm excited to bring you this week's STEM Talk. And now it's my great pleasure to introduce you to Gary Green of the Systems Analysis and Simulation Subdivision, who's here to talk with us about complex numbers and Mandelbrot sets.
Thank you, Michelle, and thank you all for joining us today. This talk is targeted to students, although you parents can certainly listen in. My objective is to show you some of the magic that can be found in mathematics. I hope to surprise you and maybe interest you in mathematics a little bit. I developed this talk as part of a series of classes I give to 4th and 5th graders, so I'm sure that there are some students who are younger than 4th grade. In case I go over some material that you don't understand, please don't hang up on me. Hang around. I promise you it will get interesting. And in the same vein, those students who are older than 5th grade, I may present some material that you know all about and think are boring. I'd ask you to hang around too, because there is some interesting stuff involved. So I'm going to develop some mathematics as part of this talk. There will be no test at the end of the talk, so you don't need to learn it. So today I'm going to talk about some topics. I'm going to talk about a new number that we will invent. I'm going to talk about exploding numbers and iteration. That's a process of doing something over and over again. I'm going to talk about a Frenchman who found out about exploding numbers, a guy by the name of Mandelbrot, and I'm going to talk about Mandelbrot sets, an extension called fractals, and their uses. But first, I need to develop some mathematics for you, and so negative numbers, some of you may know about and some may not. Suppose it's 2 degrees outside, but the temperature drops 5 degrees. How cold is it? And the answer is -3 degrees. -3 is a negative number, and if you look at the number line, there's number 2, and if you go 5 degrees lower, you get to -3. So -3 is just as good a number as +3. It's just to the left of 0, and we need to do a little bit of arithmetic with negative numbers. We can add, subtract, multiply, and divide them, but all we're going to do today is talk about multiplication. And I think most everybody knows that if you multiply 2 positive numbers, you get a positive number. What happens if you multiply a negative number times a positive number? Well, the answer is a -6 if it's -2 times 3. So if the numbers have different signs, the result is negative. If you multiply 2 negative numbers together, you get a positive. So -2 times -3 is equal to 6. So in general, the rule for multiplying numbers together, if one or both are negative, is multiply the numbers as if they're positive numbers and then assign a plus sign or a negative sign. So another item I'd like to develop for you is to say that numbers can be defined by equations. And this line of thought didn't start until about 500 years ago, when mathematicians were changing over from geometric ideas in which you drew figures to equations that came from the Arabs in algebra. And so let's take a sample equation, 2 times x minus 8 equals 0. And the question is, what is x? What number, when you multiply it by 2 and subtract 8 from it, gives you 0? Let's see, if x is equal to 1, is that an answer? No, it's not, because 2 times 1 is 2. If you subtract 8, that's certainly not 0. And if you try a few numbers, you will find out that x is equal to 4, because 2 times 4 minus 8 is equal to 0. So this equation, in a certain sense, defines the number 4. Let's take another equation. 5 times some number minus 3 is equal to 0. What is that number? And it turns out that the number is 3/5, a fraction, because 5 times 3/5 minus 3 is equal to 0. So you have equations that not only define whole numbers, but you have equations that define fractions. And here's an interesting equation. A number times itself is equal to 9. What is x? Well, let's see, is x equal to 1? No, because 1 times 1 is equal to 1, and certainly not 9. And you students out there may have guessed that x equal to 3 is an answer because 3 times 3 equals 9. But we know, because we know about negative numbers, that there's another answer, minus 3, because minus 3 times minus 3 is equal to 9. So here's an interesting equation that has two answers, which may surprise some of you students. This is a very interesting equation. X times x is equal to a minus 1. And the question is, what is x? Well, let's see. This gets to be interesting because we have a problem solving this equation. X has got to be either positive or negative. It can't be 0. Why can't it be 0? Because 0 times 0 is equal to 0, and that's certainly not minus 1. So, if x is positive, you multiply two positive numbers together and you get a positive number. And if x is negative, multiply two negative numbers together, you still get a positive. And so this equation just doesn't have an answer. Well, about 500 years ago, an Italian mathematician by the name of Cardano said, I'm not satisfied with this. I've got to have an answer to an equation like this. And so he decided to invent a new number. And the new number is called I, or imaginary, because Cardano and other mathematicians at the time just couldn't imagine what kind of a number, when you multiply it by itself, gives you a minus 1. So they said, this isn't a real number. This is an imaginary number. The good news is the multiplication table for I is really simple. You don't need to know that. And Cardano and others came up with what are called complex numbers. They have two parts. They have a real part. Those are the numbers in green. And they have a complex part, an imaginary part, the numbers in red. So complex numbers have two parts, a real part and an imaginary part, and together they make up a set of complex numbers. Okay. All the numbers that we know about live on the number line. Where do we put 2? Right there. Where do we put a half? Right here. Where do we put minus 33? Well, it's somewhere off the line, off the chart, but it's there somewhere. And the big question is, where do we put I? And I is such a strange number, it doesn't fit on the number line. And so mathematicians came up with a way to draw a picture of I. And what they did is they said, here's the real axis, where most of you students know about numbers. And they said, let's draw another axis at right angles to it called the imaginary axis. Now we're going to put I not on the real axis, but on the imaginary axis right up there. So that's where I is. And we should pause and think about this a little bit. I is such a strange number that it doesn't live where all the other numbers live. As a matter of fact, let's take a point out in the plane. Its name is C. And notice that C is 2 units away from the imaginary axis and 1 unit up from the real axis. And so its coordinates for those students who have studied this already are 2 and 1. But we could also think of C as a complex number. It's 2 plus 1I, or because mathematicians are kind of lazy, we don't write the 1. You could say just 2 plus I. And so this complex number then is like an arrow that starts where the axes intersect and goes out to the point 2, 1. So this is a picture, if you wish, of the complex number C. There are all kinds of complex numbers on the plane. Here's one, another, a third, and they all have names. How about the complex number D? Well, its name is a minus 1 plus 3I. And where did that come from? It came from the fact that the point is 1 unit to the left of the imaginary axis, so that's where the minus 1 came from, and it's 3 units up from the real axis. That's where the 3 came from. So now we have a whole new set of complex numbers, and before I go on, I will pause. Are there any questions?
Nothing so far.
Okay. Very good. Well, mathematicians thought, well, what good is it to have these numbers? Can we do anything with them? And the answer is yes. We can add and subtract complex numbers, and it's rather easy. It's like taking the components of the numbers, the 4i and the 5i is sort of like 4 apples and 5 apples. How many apples do you have? 9 apples. The 4i plus 5i is 9i. And of course, 2 plus 4 is equal to 6. So when you add those two complex numbers, you get 6 plus 9i. In the same manner, if we subtract 3 plus 2i from 6 plus 8i, we subtract the imaginary parts from one another. 2i from 8i is 6i, and 6 minus 3 is 3. And not content to stop it with addition and subtraction, mathematicians decided they would multiply and divide complex numbers too. And multiplying numbers is sort of like multiplying multiple digit numbers. You take the 4i and multiply it by another 4i, giving you 16, that's 4 times 4, times I times I. And we will also multiply 2 times 4i and get 8i. In a similar manner, we take the 3 and multiply it by the 2 plus 4i and get 6 plus 12i. And when we add all these up, we get 6 plus 20i, that's 8i plus 12i, minus 16. And you might ask, where did that minus 16 come from? I thought it was 16 times I times I. But remember, I times I is just a minus 1. So the answer is minus 10 plus 20i. Division of complex numbers is a little complicated, and we don't need it today, but I will tell you that the quotient of these two complex numbers is a minus the quantity 14 plus 15i divided by 5. Okay. Enough of this learning about numbers, complex numbers, and negative numbers. What we're really interested in today is in exploding numbers, and what we're going to do is create sets of exploding numbers. We're going to learn when some numbers explode and when some numbers don't. And so what we do is we pick a starting number, S, and S stands for starting. Then we're interested in whether S will explode or not. We will set a newer number, C, equal to S. And we're going to generate a whole string of new C's using the formula C times C plus S with an arrow goes to C. And most of you have never seen a formula like this. This is an iteration that we're going to do over and over again. And the way this works is you start with an S. You set C equal to S to start with. You generate a new C. And I'm using colors so that you can differentiate between the C's. You take the new C, you stick it into the formula, multiply it by itself, add S, and get a newer C, and over and over and over again. And let's do an example so you can see what's going on. Let's start with S equals 1. We want to know whether S equals 1 explodes or not. Now, our first C is just equal to S. Excuse me. Now, the new C, the purple C, is nothing more than a product of the old C times itself plus S. And where did the old C value come from? It's 1. And where is S? S is always 1. So 1 times 1 is 1, plus 1 is equal to 2. And we now have a new value of C, a purple value of C. Well, let's not quit there. Let's get a green C. We take the most recent value of C, 2. We take the original value of S, 1, do the arithmetic, and we get a 5. So now we have an orange C, a purple C, and a green C. Let's get a blue C. We'll start with a 5, add 1 to it, and get 26. And do you see the pattern? The next C, the brown C, is 26 times 26 plus 1, and that's a big number, 677. And if we went one more number, another color of C, it would be over 450,000. So S equals 1 explodes because this series of S's, of C's that we've created gets larger and larger and larger. Are there any questions?
We do have a question, and it was, what do you mean by explode in terms of the numbers? How does a number explode?
The number explodes if the sequence of C's, like I've gone through here, gets large. And it's up to you to decide what explodes means. You could use 100,000 or maybe 500,000. It's up to you. But it's obvious that this sequence of C's is going to get bigger and bigger and bigger till it's just huge. You might ask the question, do all numbers explode if we use this explosion formula? Well, let's try S equals -1. So the first value of C is also equal to -1. We get a green C from the orange C by multiplying the most recent value of C, -1 times -1, and subtract S from it. And we've learned that the product of two negative numbers is positive, so this is 1 minus 1, or 0. So the first C was -1. The second C was 0. The third C, a purple C, is equal to -1. And the next C, the red C, is equal to 0. So we have a pattern here. And I would ask my audience to tell me what you think the next number in this pattern will be. And you should have come up with the pattern -1, 0, -1, 0, -1, 0, and so on forever. And so the number -1 does not explode. As a matter of fact, it bounces back and forth between 0 and -1, 0 and -1. So we could try other numbers, but I think you get the idea. We generate a series of C's. We see if they get large. And if they get large, we say they explode. And if they don't get large, we say they don't explode. Let's talk about Benoit Mandelbrot. He was a French mathematician who worked at IBM, and he studied whether numbers explode, and he found some strange results. As a matter of fact, he found that numbers larger than a quarter explode, and numbers less than a -2 explode also. But in the middle, the numbers don't explode. Well, that's sort of ho-hum. What made Mandelbrot remarkable is that he said, let's do this for complex numbers. And that's one of the reasons I developed complex numbers for you. And so I'm going to show you with just one complex number how you tell whether it explodes or not. And so here is a set of C's that I've generated for you. The first value of C for I equals 0 is just the number we started with, the 0.2 plus 0.1i. How do we get the next value of C in row 1? Well, we use the explosion formula. We take the most recent value of C, that's in row 0, you multiply it by itself, and then add the S that we started with. Okay? And so if we fill in those numbers, there they are. And if we do some arithmetic, which is boring, but we need to do it, we get 0.23 plus 0.14i. That's the next number in the table. How do we get the number in the table on row number 2? Well, we take the most recent value of C in the row above it, multiply it by itself, add the starting value, do some arithmetic, and we get 0.233 plus 0.164i. That's the number in this table. And the next number comes from the number above it, and so on, and so on, and so on. And trust me, those numbers are right. And what I'd like to do now is draw a picture of these numbers. The first number is at 0.2 plus 0.1i. That's where it lives. It's 0.2 of a unit away from the imaginary axis and 0.1 of a unit up from the real axis. The next number is 0.23 plus 0.14i, and it's up about here. So it looks like these numbers are getting bigger. As a matter of fact, the next number is bigger yet. I wonder if this is going to explode, and the answer is no, because what happens, is that these numbers take a turn and they start spinning around. It's sort of like a whirlpool. And they spin round and around and around, and eventually they settle out at a number that's approximately this number. So in fact, the number 0.2 plus 0.1i does not explode. Okay. Mandelbrot was interested in which numbers explode and which numbers do not. And Brooks and Matelski, about 40 years ago, started testing out which numbers explode and which do not. And what they did is they picked about 1,000 numbers, all kind of at the start of the imaginary axis and real axis, and they put a star if the number did not explode. So the number 0 plus 0i right in the center does not explode. And all of these stars are numbers that don't explode. To the outside of these stars are numbers that do explode. And one question the curious might ask is, why does this shape have such a funny boundary? Why isn't it smooth? Our number 0.2 plus 0.1i lives about there. And so people scratched their heads over this and they said, what in the Sam Hill is going on with these numbers? Well, Brooks and Matelski only computed about 1,000 points, and that's because in the late 70s when they did their work, computers were slow and they couldn't test a lot of numbers. But even today's phones are much, much faster. We have much faster computers, and now rather than the roughly 1,000 points that Brooks and Matelski worked on, we can test billions of points, all closely spaced, much more closely spaced than Brooks and Matelski did. And so now we can get a better picture of what's called the Mandelbrot set, and it looks like this. Wow. What a funny shape. The Mandelbrot set consists of numbers that do not explode. Anything that's in black, this funny shaped object, will not explode, and anything outside the object will explode. And these objects have names. This thing is called a cardioid, but I'd rather call it a heart. And then these things on the outside are called bulbs. And notice that there's a bulb centered at -1. There's another bulb at the top of the cardioid. And there are bulbs marching down, 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 down into this valley. And there are also bulbs marching down, down, down into this valley too. So this is very curious indeed. But we are interested in comparing this with what Brooks and Matelski did. So that's what they did. Now the current modern day Mandelbrot set that includes millions and millions of points as opposed to the 1,000 that Brooks and Matelski showed. One last look at Brooks and Matelski. And now let's start examining the Mandelbrot set.
Gary, we have a question from Leanne's son, and he asks if that is a factorial.
Pardon me?
Leanne's son is asking if that is a factorial.
A factorial? Oh, a fractal. Yes, it is. So, one of the things that we noticed is that we have all of these things. These are called bulbs. And you get a series of bulbs marching down into the valley. And if you look at this bulb on the top, it has a bulb on the top of it. And that bulb has a bulb on top of it. And if we expanded this, that bulb would have a bulb on top of it. And it calls to mind a quotation from Jonathan Swift that fleas have fleas, that have fleas, have fleas forever. And geometric shapes that have this property, that they have features that repeat and repeat and repeat are called self-similar. And the Mandelbrot set has areas that are self-similar and areas that are almost self-similar, but more about that later. So I'll remind you that points inside the Mandelbrot set are safe. They don't explode. But points in other areas, like my red dot here, or a red dot here, or this red dot, explode. And there are some names for these features. One name is called the Seahorse Valley, and the other is an Elephant Valley, and you'll understand why in a moment. Here's another picture of the Mandelbrot set. What we've done is we've colored in black all the points that don't explode. And outside that black set we've colored points according to how long it takes before they explode, how long before the series of C's gets big, like larger than 100,000 or a million or whatever number you would like to pick. So a dark area means that points out here explode quickly. Maybe it only takes 2 or 3 iterations before they're very, very large. But down in Seahorse Valley, see my little dot right in the valley? That may take a long time to explode. And I thought you might enjoy seeing why this valley is called the Seahorse Valley. So I've taken a different coloring for the valley and blown it up so that you can see the detail. You can see the bulbs, but notice all the seahorses on this diagram. If you look closely, you'll see hundreds and hundreds of seahorses. Isn't that pretty? Over in Elephant Valley, you get a sequence of elephants marching along. Their bases are the bulbs, and you can see their trunks and other features of the elephants. Again, isn't that pretty? What I'm going to do now is take a strip out of the bottom Seahorse Valley. I'm going to cut it out and paste it on the next slide. So here's that strip, and it's colored dark to light. What do the different color shades mean? Well, if it's dark, it means that the point will explode in just a very few iterations. But as the points get lighter and lighter, the colors get lighter and lighter, it takes more and more iterations until you're in a practically white area. It may take millions of iterations, but sooner or later, the point will explode. Now, I'll admit I made up to 3,478,542 iterations, but it could take a very long time. So now what we want to do is take a dive into the Mandelbrot set. Oh, pardon me while I activate this. So here's our Mandelbrot set again, and it's colored according to how long it takes a point to explode. And before I start on this animation, I'm going to pause and ask, are there any questions?
No more at this time.
Okay, very good. So what I'm going to do now is dive into the Mandelbrot set. I'm first going to point out that this bulb is a bulb that's half a unit wide. This point on the left edge is minus 1.25, and the point on the right edge is minus 0.75, so it's 0.5 across. Now what I'm going to do is zoom in. I'm going to magnify this area right here 10 times. And you can see this march down into Seahorse Valley, and there are some figures marching down into the valley also. And notice what has happened. The Mandelbrot set consists of all the points that are black, and we've colored outside the Mandelbrot set according to how long it takes until a point explodes. So if it's not black, it's going to explode. If it's a very, very light color, it may mean that it takes a million iterations before it explodes. Here, this faintly dark may take only 500 iterations before it explodes. But we're going to blow this up and see what we see. So now we've blown this up 50 times. And we see some bulbs. Now we're starting to see some traceries. Some very exotic patterns. And this is part of the Mandelbrot set. It comes out, and you can walk along a curly line until you get to this point. Let's blow that up again. So now we've magnified this 500 times, and we've got all these little tendrils reaching out. This is all part of the Mandelbrot set, but let's blow this area up. We're now at 5,000 times magnification, and lo and behold, what do we see? We see the Mandelbrot set all over again, but this time it's been magnified 5,000 times, and it's been rotated a little bit. It's not exactly the Mandelbrot set, but pretty close to it. Well, let's blow this area up and see what we see. We're now at 20,000 times magnifications, and this is a bulb that was on the other bulb. Let's blow this up and see what we see. This is a figure that looks vaguely like a Mandelbrot set, but it's not exactly. It's almost. So although fractals can be self-similar, not all areas in the Mandelbrot set are self-similar. This is a sort of self-similar area. Let's blow this up from 100,000 times magnification to 500,000 times magnification. And here we have this almost Mandelbrot set. Let's blow up this. And look at all the tendrils that go out. These are all part of the Mandelbrot set. Let's blow this up. We're now at 5 million times magnification. Let's go to 50 million times magnification. And finally, one more magnification, where we get a set that sort of looks like the Mandelbrot set. Now we've magnified this area 250 million times. And as a point of reference, this window is less than 1 millionth of a unit apart. Remember that first bulb was half a unit wide? This whole window is 1/1,000,000th of a unit wide. And along the way, we've seen lots and lots of interesting patterns as part of the Mandelbrot set. So people are very interested in this, and you can go online, Google Mandelbrot sets, and see different pictures, all of which are very interesting. But Mandelbrot actually didn't draw any pictures. He was interested in other things. He was interested in determining whether if you put a pencil down on one point in the Mandelbrot set, can you drag it to another point without getting off the Mandelbrot set, without touching another color? And the answer is yes. You can drag from one Mandelbrot point to another Mandelbrot point without getting outside the boundary. Another way to ask the same question is, are there any islands in the Mandelbrot set? And the answer is no. What's really, really curious about the Mandelbrot set is you might wonder, what dimension is it? Is it a line, one dimension? Is it an object like a square and the interior of the square, 2 dimensions? What is it? And it turns out the Mandelbrot set is 2-dimensional, but what's also interesting is that the boundary of the Mandelbrot set also has dimension 2. It's the same as the interior of a square. And that blows my mind. You know, I think about the boundary of a square. If I take those lines and cut them, all they are is a line segment. It's 1-dimensional. But somehow the boundary on the Mandelbrot set is 2-dimensional. Really strange. Before I continue on, are there questions?
We do have a question from James, and he asks, what is the application of this set of exploding and not exploding?
Boy, what a good time to ask that question. Let me show you some stuff. What you saw is an example of a fractal, and there are many different kinds of fractals. Mathematicians have been studying this material for almost 100 years before Mandelbrot got involved. A Swede by the name of Cook invented some snowflakes that I would invite you to look at, but there are lots of them. And fractals are used in many places. And one of the most obvious that we all are aware of is cell phone antennas. If you use just a piece of wire for an antenna for a cell phone, it should be about 8 inches long. It varies according to the kind of signal you're getting, but about 8 inches long. And if you look at your cell phone, it doesn't have a wire that's 8 inches long because it just won't fit. So what people do is use fractal geometry to produce antennas that work in a small area. And what they do is they take a piece of metal about the size of a postage stamp. So what I've done is I've taken that postage stamp and I've blown it up, magnified it a whole bunch of times. So you have to remember that we're starting with something that's small, like a postage stamp. And what we do is that we cut out the middle of the postage stamp. We stamp out the metal, so now we've got a piece of metal with a hole in the middle. That leaves us with 8 squares, and guess what we do? For each of those squares, we cut a hole out. So now we have 9 holes, and we take smaller squares and punch out those holes, and we can take even smaller squares and punch out those holes. And so what you get is an antenna that looks like a piece of metal with a bunch of holes punched in it, and this is called a Sierpinski square, and that's what's inside your cell phone. That's what's inside GPS receivers, or maybe inside GPS receivers. What other applications are there for fractals? Well, computer chips get hot, and we need to carry the heat away from the hot spots so that they can cool down. So what happens is that you coat the tops of the processors with a thin coat that has this pattern, and right in the middle of the pattern is where it's hot. And so these blades that go out from the center carry the heat out. And if we take one of these blades, notice there are paths in between them that branch and branch again and branch again and branch again. The more branches you have, the more surface area you have, and the better you dissipate heat. So these blades carry heat out to a place where the heat can be dissipated. And while this is not a true fractal because there are only a finite number of branches, it's very similar. Aerospace uses fractals for cloud models. Suppose you have a weather satellite and you'd like to see how it works. Well, you need to have clouds to simulate so that you can evaluate how well the weather satellite works, and you can use fractals to generate clouds. And here's an example of clouds that are generated for an aerospace application. There are lots of applications in biology. Animals travel along paths, but when the paths get clogged up or something, they will branch and branch and branch again. Plant roots start with big roots and split and split and split, and blood vessels also branch. Finally, there's art, and there are many examples of art that involve fractals, but this Barnsley fern is a good example. What you see looks to be just a picture of a fern, but if we take a closer look at it, this is a fern, some fronds that were built by iteration. Each frond is made up of smaller fronds. So the teal frond, I've identified a red subfrond and a blue subfrond. And if I look at the red subfrond, it has sub-subfronds that look very much like the red frond. And if I take the sub-subfrond and break it up, you get the idea. You get branches and branches and branches. And what Barnsley did is he made this interesting by curling fronds and changing their size and the direction they point a little bit, so you get this very pretty picture. One more example of a fractal image that doesn't at first glance look like a fractal, but this is indeed a mountain and valley constructed from fractals. Now, people have worked hard to make this look natural by adding fog and blue sky, but this is nonetheless a fractal image. So, what have we learned today? Well, for those of you who have never heard of them before, there are these numbers called complex numbers. They live on the plane, not the line. We can do arithmetic with them. And following Mr. Mandelbrot, complex numbers may explode under this explosion formula, and they create very interesting patterns. These are examples of fractals. Fractals have lots of uses. I didn't have time for all of them. So one of the things that I would hope that you would carry from this discussion is that mathematics can surprise you and it can be fun. And if you would like to read more, here's a set of references. If you want the real mathematics, Mike Barnsley's book, Fractals Everywhere, has the full and gory details. This is not a book for amateurs. And again, if you just Google Mandelbrot sets, you can pull up all kinds of pretty pictures and learn much, much more. So with that, I will thank you very much. I would also like to thank the people who have helped me put this talk together from the Aerospace University, iLab, Corporate Communications, and even out of my own subdivision. They've made it easy for me to give my talk, and they've provided lots of help. So thank you very much, and I will turn this back to Michelle.
Thank you, Gary. We'll definitely be Googling to see more sets. And thank you for joining us today. A big thank you to Gary again for taking time to be here. For employees, you are welcome to enter this time into the TLC as external learning for learning credit. For more information on how to do so, please visit the TLC and go to your training transcript page. Remember that this session is being recorded, and you'll be able to find it on AU's STEM Talks website or on the Aerospace Corporation's YouTube channel in the near future. We want to continue to bring you STEM Talks, so if you have any ideas for future presentations you would like to propose, please contact us. We'd love to hear from you. Thank you for joining us today, and keep an eye out for next week's STEM Talks on Math as a Universal Language with Patrick Yee. Hope to see you there again soon. Thank you.